In this video, we'll work through some examples calculating the sum of squares, variance, and standard deviation. Now, it's important to remember, especially if you're coming back to this video from later material, that we're using the descriptive statistics formula for the variance and standard deviation with n in the denominator. These estimates for the variance and standard deviation would only be appropriate for describing our sample, not for estimating the population variance or standard deviation. Let's start with an example based on the following data. We have 6 quiz scores with values of 15, 6, 9, 5, 6, and 13. These scores have a mean of 9. We then need to subtract the mean from each individual score, so we have 15 minus 9, 6 minus 9, 9 minus 9, 5 minus 9, 6 minus 9, and 13 minus 9. This gives us values of 6, negative 3, 0, negative 4, negative 3, and 4. These are our deviations from the mean. We know that if we just add these up, they'll sum to 0. The sum of the deviations from the mean always sums to 0 because the positive and negative values always cancel out. So we have to square these values to get rid of the negatives. That gives us 36, 9, 0, 16, 9, and 16. These are our squared deviations from the mean, or just squared deviations for short. We add these up to get our sum of squared deviations from the mean, or sum of squares, which we can abbreviate just as SS. In this case, they sum to 86. Our sum of squares is 86. You can think of the sum of squares as reflecting the total variability that exists in our sample. But remember, because it's a sum, the larger our sample size, the larger the sum of squares will be, regardless of how much actual variability there is from individual to individual. If we have a huge sample, even a small amount of variability from person to person on average is going to ultimately add up to a large sum of squares. Therefore, the variance takes the sum of squares and divides it by the sample size in order to reflect an average variability in the sample. Well, an average squared variability in the sample. If we divide our sum of squares of 86 by our sample size of 6, we calculate our variance to be 14.333. Because this is our descriptive variance formula, we represent the variance with the capital letter S squared. Again, you can think of the sum of squares as the total squared variability, while the variance is the average squared variability. Okay? We're almost there. The last step is to recognize that because we're talking about squared variability, variance alone really doesn't work as that yardstick to measure how large something is. Think back to our example of a 2-kilogram difference in the weight of our pet. Is 2 kilograms big? Well, it depends on whether our pet was a rhino or whether our pet was a grasshopper. So we take the square root of the variance to estimate the standard deviation. Because this is our descriptive statistics formula, we represent the standard deviation with the capital letter S. The standard deviation provides us with the yardstick to measure how large things are. We'll get into doing just that in upcoming videos. Now again, the variance and standard deviation formula that we've calculated with n in the denominator are descriptive statistic formulas. These are just for describing our sample, not for making inferences about the population or for estimating the standard deviation or variance in the population. Okay? Let's go through another example. This time we'll have 5 scores with values of 5, 5, 8, 9, and 13. Their mean is 8, and we subtract the mean from each score. So we have 5 minus 8, and 5 minus 8, and 8 minus 8, and 9 minus 8, and 13 minus 8, which gives us -3, -3, 0, 1, and 5 for our deviations from the mean. We square these deviations from the mean to get our squared deviations from the mean, which are 9, 9, 0, 1, and 25. We then add these up to get our sum of squares, which is 44. Think of that again as reflecting the total variability in our sample. We divide by n in order to get the variance, s squared, which we can think of as reflecting the average variability in our sample. So the variance is the sum of squares 44 divided by n, 5, or 8.8. Finally, we take the square root of the variance to calculate our standard deviation s, which is our yardstick for measuring how large things are, or how large differences are, or how large effects are. The square root of 8.8 is 2.966, so our standard deviation is 2.966, which does seem to reflect how spread out the scores are around our mean. Okay, pretty straightforward once you get in the groove of things. Now, again, ultimately, the important thing is conceptual. That the standard deviation is that yardstick that we can use to measure how big things are. And the sum of squares is an indicator of the total variability in our sample, while the variance is an indicator of the average variability in our sample. Now, of course, when we talk about the variance and sum of squares as indicators of variability, we have to remember that we're talking about squared deviations from the mean. Okay, let's do one more practice problem that highlights this point and the implications. To do this, let's keep the same values we had last time, but multiply each of them by 1,000. So we have 5,000, 5,000, 8,000, 9,000, and 13,000. Their mean is now 8,000, 1,000 times larger, no surprise there. We subtract the mean from each score, so we have 5,000 minus 8,000, and so on and so on and so on. That gives us -3,000, -3,000, 0, 1,000, and 5,000 for our deviations from the mean. We square our deviations from the mean to get our squared deviations from the mean, which are 9 million, 9 million, 0, 1 million, and 25 million. Notice these got huge in the process. We then add these up to get our sum of squares, which is 44 million. Notice the sum of squares is 1,000,000 times larger because the scores were 1,000 times larger, and we squared them. We then divide by n in order to get the variance, s squared, which is 8.8 million. That's still huge given our scores ranged from 5,000 to 13,000, and it really highlights the point that when we're talking about variance, we mean squared values of whatever our units are. So our scores are 1,000 times larger, but the variance is 1,000,000 times larger. Finally, we take the square root of the variance to calculate our standard deviation s, which is 2,966. Notice the scores are 1,000 times larger, and the standard deviation is also 1,000 times larger. So it does continue to line up perfectly with the spread that we see in our scores around the mean. Okay? So again, remember that the sum of squares and variance reflect the variability in terms of squared units of whatever we're measuring, while the standard deviation is still in the same units or scale size of whatever the original variable was. That's why we can use the standard deviation as a yardstick for that variable. Hopefully after doing a few of these, you can see how the sum of squares and variance and standard deviation are all related, and they're not that hard to calculate or conceptually understand once you have the hang of it. Okay? Bye for now.